Alright folks, in this video we're going to review three important topics we learned in College Chemistry 1. The first one is the bond polarity, the second one is Lewis structure, and the third one is molecular polarity. Let's see bond polarity first. What does it mean? It means whether a bond is polar or nonpolar. If you have a polar bond, the bond would have a negatively charged end and positively charged end. Let's use this table to demonstrate how we use the electron negativity difference. Okay, how we use the electron negativity difference delta En to identify whether a bond is polar or nonpolar. If you have a delta En between 0 and 0.4, we said that this bond is going to be a nonpolar covalent bond. One example here is a chlorine gas, okay, chlorine molecule, because the two chlorines have the same electron negativity. The electron negativity difference between the two atoms is 0, so they share electrons equally. Okay, so this bond is going to be a nonpolar covalent bond. If the electron negativity difference is in between 0.4 and 2.0, we said that the bond is going to be a polar covalent bond. Example here is the hydrogen chloride. Because the electron negativity difference between hydrogen and chlorine is so high, the chlorine will attract most of the electron negativity to become negatively charged. And in the hydrogen, it has a much less electron negativity than chlorine, so it cannot compete with the chlorine in this to share electrons. So this side would be positively charged. And how do we label those kind of polar covalent bonds? We draw an arrow, okay, going from the positive side to negative side, and we use the cross sign on the positively charged side to identify the end, the positively charged end. Okay, so this is how we label the bond polarity. All right, how about those molecules with electron negativity difference larger than 2.0? In this case, it's going to form ionic bond. One example here is a sodium chloride. When the two atoms interact with each other, sodium is going to lose the 3s1 electron to chlorine to form sodium cation. Chlorine get 1 electron to form the chlorine anion. We don't use dash line between the two atoms because dash line usually means covalent bond. You just need to draw the cation and anion separately, and between these two, it's just pure electrostatic interaction. Okay, so it's going to be an ionic bond. And in chemistry, we do have a parameter, dipole moment, mu, to measure the bond or molecular polarity. Okay, and the unit of this dipole moment is d, the dBs. And what's the connection between the dipole moment, electron negativity difference, and the bond polarity? Here is a trend. If you have a larger electron negativity difference, delta En increase, that will give you a larger or greater dipole moment, and that will give you a greater bond polarity. The bond polarity will also increase. Okay, so this is a general trend. And of course, when you have a smaller electron negativity difference, then the mu would decrease, would be smaller, and of course the bond polarity would be smaller. Okay, let's say this table: chlorine, chlorine fluoride, hydrogen fluoride, and lithium fluoride. The electron negativity difference is increasing from top to bottom. Okay, and that will tell you the dipole moment will increase. So if I want you to predict the bond polarity for these four molecules, you will see, based on this trend, you will see that go from top to bottom, the bond polarity increase. Okay, so this is the bond polarity. Now let's see Lewis structure. The reason why I want to review Lewis structure is it is important. It is very important for you to identify the intermolecular forces later on in chapter 11. So I do need you guys to know how to draw Lewis structure. This slide shows us the general procedures to draw the Lewis structure, and again, it's from your textbook. Let's use the example to demonstrate how we use those guidelines to help us. The first example is Ch3Cl. Okay, first procedure is to write the correct skeletal structure for the molecule. And two things that I need you to know in this in the first procedure. The first one is you need to know how to identify the central atom. Usually, the central atom would be the atom with less electron negativity. Okay, so for this molecule, okay. Let's finish this. The second thing. The second thing is the hydrogen is always terminal or surrounding atom. So in this molecule, you have 3 hydrogen, 1 chlorine, and 1 carbon. Hydrogen always a surrounding atom. Chlorine and the carbon has less electron negativity than chlorine. So the carbon would be the central atom. So what you need to do is just write the other 4 atoms around the carbon and draw single bond for each pair. And this is a skeletal structure for this compound. The second procedure is calculate the total number of the valence electrons. You have 1 chlorine, 1 carbon, and 3 hydrogens. For chlorine, because it's from group 17, so it will give you 7 valence electrons. Carbon, group 14, so 4 electrons. 3 hydrogens, okay. Each one of them will give you 1 electron, so 3 times 1. Okay, it will give you total 14 valence electrons. One thing I do need you to know here is if you have a polyatomic ions, then you need to add the negative charge or subtract the positive charge. This is a neutral atom, so we don't need to worry about this right now. I'm going to show you one example later on. Okay. Now let's go to the step 3. Distribute the electrons among the atoms. When you do this, you need to make sure that each atom should have either 8 electrons or 2 electrons. When we talk about the 8 electrons, that means octet. 2 electrons, duet. Duet, that is only for hydrogen or helium, okay, or helium. And for the other atoms, they should have 8 electrons. Now, let's take a look at this structure. Now, hydrogen, because each hydrogen shares 2 electrons with carbon, so hydrogens are happy enough. But for chlorine, it's not happy because it only has 2. And so you need to add 6 more electrons on chlorine. Okay, and when you distribute the electrons among the atoms, you make sure the surrounding atoms have 8 electrons or 2 electrons first. And in this case, you make sure chlorine has 8 electrons first. Now, when you count the electrons, the total number of electrons we used in this structure, you would see that we've already used all of the 14 electrons. Okay, so this is the Lewis structure of this CH3Cl. Let's see one more example. Water, H2O. The first procedure, identify the central atom. Because hydrogen, okay, let me label the number of the examples. The second example, water, because hydrogen is always a surrounding atom, so you only have one option, and that is oxygen as a central atom. And again, you draw the skeletal structure, and then you count the valence electrons. 1 oxygen, 6. 2 hydrogens, 2 electrons. So total you would have 8. Okay, total you would have 8 electrons. Now, when you look at the structure, hydrogens are happy enough because each one of them has 2 electrons, but oxygen only has 4. So you need to make sure that it has 8 electrons. How do we do it? We add 4 electrons on oxygen, and that means we would have 2 lone pairs on oxygen atom. Now, when you count the electrons, we've already used 8 electrons, oxygen 8 electrons, 2 hydrogen 2 electrons each. So everybody's happy for this molecule. So this is a Lewis structure for water molecule. Now, the third one I want to show you here is the CO2 minus, CO3 2 minus, CO3 2 minus. Okay, and in this example, I'm going to demonstrate how we form the double bond because we really haven't used the step 4, and we haven't talked about the polyatomic ion here. Now, when you look at this molecule, this is a polyatomic ion. Okay, it has two negative charges. Now, it has only 2 atoms. The 2 elements. One is carbon, the other one is oxygen. So carbon has less electron negativity than oxygen, so apparently the carbon would be the central atom and oxygen would be the surrounding atom. Okay, and then you draw the single bond for each pair. Okay, so this is a skeletal structure. 2 minus. Now here, let's count the total valence electrons. 1 carbon, 4 electrons. 1 oxygen is 6 electrons. But because you have 3 oxygen, so 3 times 6 valence electrons, it gives you 18. And remember, if the ion is negatively charged, you do need to add the charge when you count the total valence electrons. Okay, because this is so for this CO3 2 minus, you need to add 2 more electrons. Okay, so you do the calculation and you'll find that total it has 24 valence electrons. Now let's distribute the electrons among the atoms. And again, when you do this, you make sure oxygen has 8 electrons first. So you add 6 electrons for each oxygen. Okay, so all right. Okay, so this is the step 3. Now, when you count the step after you finish this the step 3, let's count the valence electrons. 80 electrons here, 80 electrons here, 80 electrons here. So you've already used all of the 24 electrons. But when you take a closer look at the carbon, carbon has only 6 electrons, so it's not happy. How do we fix this problem? You form double bond, which means one of the oxygens will share 1 lone pair to form a double bond. Okay, so let me use the eraser to erase one of the double bond here. Let's see. Let's assume that this oxygen will form double bonds with the carbon. Okay. All right, this is how we do it. Now, when you check all of the 4 atoms, all of them have 8 electrons. Everybody's happy, and this is the right Lewis structure of the CO3 2 minus. Okay. All right. Now, the third topic it would be the molecular polarity. And how do we find out the molecular polarity? We have 2 ways. The best way is to use the vector addition. Okay, you find out the dipole moment for each bond and then you add them together. And the second, okay, so let me write it here. So this is the first one, the vector addition. Okay, the second way to identify with molecular polarity is following the flow chart here. Okay, let me use these 3 examples to demonstrate how we do the vector addition. The first example is the hydrogen chloride. Hydrogen chloride, you only have 1 bond. So in this case, the bond polarity equals to the molecular polarity. The bond polarity is from the hydrogen side to chlorine side, and that also represents the molecular polarity, because the bond polarity is not zero, so the molecular polarity is not zero, so this molecule is polar. All right, so this is the molecule with only one bond. How about the molecule with more than one bond? For instance, water here. And water, we've already drawn the Lewis structure of water molecule, and we will see that you would have two OH single bond. For each one of them, you have bond polarity pointing from the hydrogen side to oxygen side. Then, if you are using the vector addition to find out the net to find out whether this molecule is polar or non-polar, you need to do this. Okay, so you have two bond polarity pointing to the oxygen, so you add these two vectors together. How do we do it? You draw the square and you add them together, and that's how. And this one here is the net dipole moment of water molecule, because it's non-zero, so water is polar. Okay, and how about the carbon dioxide? Carbon dioxide 2CO double bond, and after you identify the bond polarity, you can see that they are pointing to the opposite direction, and when you add them together, they cancel each other out. So the net dipole moment is zero. So this compound is nonpolar, okay, which means the molecular polarity of the carbon dioxide is zero. So this is a nonpolar molecule. As you can see, the vector addition could be very intimidating, and let's try the second one. The second one, the flow chart, is easier. Okay, it's less accurate, but it's easier, and I think it's good for our college chemistry 1 and college chemistry 2. So let's try some examples. Okay, and before you use this flow chart, you need to draw the Lewis structure first. Okay, let's use a water molecule to demonstrate. Water molecule, 2 hydrogen oxygen single bonds and 2 lone pairs on the oxygens. Now you need to ask yourself questions when you follow this when you use this flow chart. The first question is, are all electron groups of the central atom identical? Which means the electron groups here means either lone pairs or covalent bonds. Okay, so for oxygen here, it has 4 electron groups. You have 2 lone pairs and 2 single bonds. Apparently, the 2 lone pairs are different from the two single bonds. So the answer is no. Okay, the electron groups of oxygen are not identical. So you go this side. And the second question you need to ask yourself is this molecule one of the 4 molecules here? Xenon tetrafluoride, xenon difluoride, triiodide, and tribromide. Okay. If it is not, then this molecule would be polar. If it is one of the 4 molecules, then it's going to be a nonpolar molecule. For water, it's not one of the 4 molecules are listed here, so it's a polar molecule. Okay, so it's polar. We got the same conclusion as we did for a vector addition. Let's see this example, CH4. You draw the Lewis structure and you will see that the carbon central atom has 4 hydrogen atoms. Okay. And now you ask yourself a question. Are all electron groups identical? You have 4 carbon-hydrogen single bonds around the carbon. So absolutely, the 4 electron groups are identical. Okay, so the answer is yes. So this one would be nonpolar molecule. Okay, one more example. How about, okay, let me label it. This is example 1. And is example 2. How about carbon? We did this molecule in the previous slides, and we know the Lewis structure would be something like this. Now, when you compare the 4 electron groups around the central atom carbon here, you will see that carbon chlorine single bond is different from the 3 carbon hydrogen single bonds. So the first question, are all electron groups of the central atom identical? The answer is no. Okay, so you go this way. And this molecule apparently is not one of the 4 molecules listed here, so absolutely it should be a polar molecule. Okay, should be a polar molecule. All right. Now, the question is, xenon tetrafluoride. If you use a flowchart to find out whether the xenon tetrafluoride is neutral, is polar or non-polar, apparently you need to draw the Lewis structure first. Xenon central atom, and you have 4 fluoride. Okay, my bad. Let me erase that. Okay, so you have 4 fluoride. And you have 2 lone pairs on the xenon center. And so apparently the 6 electron groups, and they are not identical, so you need to go this way. And the xenon tetrafluoride is one of the 4 molecules, so the answer is yes. So it's nonpolar. But how do we know it's nonpolar? In this way, for these 4 molecules, the way to find out whether it's polar or nonpolar is to use the vector addition. Okay, because of the symmetry of this molecule, as you can see, the xenon fluoride bonds, they are opposite to each other, and the xenon fluoride they are opposite to each other, and 2 lone pairs, they are opposite to each other. And so the dipole moment, the dipole moment of the bonds, they all cancel each other out. So the net dipole moment of the whole molecule is 0. Okay, so this is a nonpolar molecule, and you can use the same strategy, the vector addition, to figure out xenon difluoride, triiodide, and tribromide. All of them are nonpolar bonds. Okay, so these are the 4 exceptions I need you to remember when you use the flowchart. Okay, so I hope this review can help you understand how we figure out the bond polarity, how to draw the Lewis structure, and how to figure out whether a molecule is polar or nonpolar. Of course, you need practice. Okay, so here this slide shows you some recommended question for you, and whenever you got time, try those questions. And even if you know how to do all of the 3 topics, it won't hurt you to refresh your memory a little bit. Okay, so whenever you have time, try those problems, and if you have any questions, please let me know. All right,